Most of us make some sort of journey every day. To school, to the shops, or to work. Gabriel's Wharf, please.
Some journeys are very long, and some journeys are very short. Gabriel's Wharf, please, mate. Come on.
This programme is about how journeys can be analysed mathematically and plotted on a graph.
Oh,
Hello, hello, hello.
Casey, good afternoon. I'm
Good
safe at
afternoon.
last. Thanks.
What a lot of fun. Right, all you need to know is how far you travelled and how long the journey took. Now, mathematically speaking, that's distance travelled and time taken.
It certainly is. Now, what that involves then is us collecting some data, which means we have to go on some journeys. And as ever, secreted on my person, I have those said journeys.
Fabulous.
The yellow or the blue, which would
Can
you
I
like?
choose? I'd like the yellow, please.
You sure?
Yep, I'd like the yellow.
Okay, let me see what your journey is. Ah, the good news. You're going from London to Brussels on the Eurostar.
Excellent.
The bad news, you're not going to get to stop and do any shopping. In fact, you're coming straight back on the first train back into town.
Oh dear, there had to be a catch, didn't there? Okay, well, let's
Okay.
reveal what your journey's going to be.
Tell me.
You are spending the day in London with a new pop group called the Atomic Kittens.
Oh, fantastic. Very glamorous.
Fantastic. Well, you might think so, but the bad news is your day starts at 7 a.m. tomorrow morning. Not so glamorous.
Love them or hate them, pop stars have a very busy lifestyle. And when you're promoting a new record, things can get extremely hectic. Today it's my job to try and make sure the girls get to all their appointments on time. And as we go along, I'm going to be drawing a distance time graph of the journey, especially for you. To draw any graph, you need to have two axes. With the distance time graph, the horizontal axis always represents time. And the vertical axis always represents distance travelled. Now, I know that all our appointments are going to be in London today, so we're not actually going to be travelling more than 20 miles away from where we started, which means that the distance travelled axis needs therefore to go from 0 to 20. As for the time axis, well, we got here at 7 o'clock this morning. We're not going to be back at the hotel till 8 o'clock this evening, so that needs to go from 7 in the morning till 8 in the evening. And each of these squares represents half an hour of time. So that's the graph all labelled up. What we need to do now is put the first point on it. The time is 7:30. We're 0 miles from where we started, so the first point goes just there.
Making me feel that I want it.
Okay, here we go. First stop, Kenilworth Primary School.
Here we go.
It's 9 o'clock and we've travelled 15 miles to get to the school where the girls are about to perform in just a moment. So, seeing as we've got this far, it's time for us to plot the next point on our graph. It's 9 o'clock, so we need to travel along to 9 on the time axis. We've travelled 15 miles, so we need to go to 15 on the distance axis, which means that right now, we are bang, right there, easy. So that's us, but I wonder how Katie's getting on.
My journey might just be a day return to Brussels, but at least I get to put my feet up while Ben is chasing around after Atomic Kitten. Coming into the tunnel. No! I'm now in France and on my way to Belgium. So, here's the maths. For my journey to Brussels, my time axis, which is the horizontal axis, is going to need to cover the time from 10:30 a.m. to 2:30 p.m. But I'm travelling a lot further than Ben is. It's 375 kilometres to Brussels, so I've chosen to have my distance scale go from 0 to 400 kilometres. Now to plot some points. At 10:30, we were just about to leave London, and the distance travelled was 0 kilometres, which is there. At 11:30, we were just about to enter the tunnel, and the distance travelled from the starting point, London, was 115 kilometres, which is about there. At 11:50, we were just coming out of the tunnel. Each of these squares here represents 10 minutes, and the tunnel is 50 kilometres long. So that would be 165 kilometres from our starting point, London. We come across here, that's about there. The thing to do next is to draw a straight line between the points. And you'll see that you get two different slopes. Each slope has a different gradient, and the gradient of a distance time graph tells you about speed. You'll see that here the gradient of the journey before we entered the tunnel is less steep than when we were in the tunnel here. And a steeper slope, like this one, means that we're actually travelling faster when we were in the tunnel. But how fast is it travelling? Well, in 1 hour, we covered 115 kilometres. So we were actually travelling at an average speed of 115 kilometres per hour. But Eurostar takes just 20 minutes to go through the tunnel, which is 50 kilometres long. And at that rate, we would actually cover 3 times that distance in an hour. So we would be going at an average speed of 150 kilometres per hour. But enough of the maths. Now it's time to get back to the serious business of travelling first class.
For your juice.
Ah, merci beaucoup.
It's 10:30 and we really need to get the girls going so we're not late for our next port of call. But before we do go any further, then I want you to have a quick look at the graph here. Now, as you can see, we started at the hotel at 7:30 and we travelled for an hour and a half and 15 miles to get to the school where the girls have been performing. Now, for the last hour and a half, we've been in the same place, and have a look what's happened to the graph. The line has stayed the same because our distance from the start hasn't changed. Distance from the start hasn't changed, so the line is horizontal, the gradient is 0. Remember, the steeper the slope, the greater the gradient, the faster you're travelling. If the line is horizontal, it means you're not moving at all.
It's now 10 minutes past 1 and we've just pulled into Brussels station. And this is what my distance time graph looks like now. You can see that the distance we've come from London is 375 kilometres. And you can also see what the sections of the journey were. This was a part of the journey from London to the tunnel. This was a section in the tunnel. And this was the rest of the journey up to Brussels. Now, if you look very carefully, you can see that the gradient of the graph here is steeper than the gradient of the graph here. Now, what does that tell you about the average speed of the Eurostar in France and Belgium compared to in the UK? The average speed in the UK was 115 kilometres per hour, but we need to know the average speed in France and Belgium. It's a more complicated speed calculation than before, so we need to use the equation speed equals distance travelled over time taken. The distance travelled was 210 kilometres. And the time taken was 80 minutes. So the speed is equal to 210 divided by 80, which is 2.625 kilometres per minute. Multiplying by 60 to convert it into kilometres per hour gives 157.5. Which is 42.5 kilometres per hour faster than the Eurostar's speed in the UK.
After performing at the primary school, it was a short journey to a local cafe for a bite to eat. An hour later, we travelled to the Elstree studios to record Top of the Pops, where the girls told me in no uncertain terms where to get off.
I'm going to get to see you guys perform as well.
No, sorry mate, this is your stuff. We'll see everyone else. You go to the pubs? Yeah, come on.
They're not kittens, they're polecats.
After a 6.5-hour wait while the girls performed, it was time to go back to the hotel. We left Top of the Pops at 7 and travelled the same distance back to where we started at the beginning of the day. It's now 8 p.m, so where do we plot the final point?
Well, the time is 8 o'clock. We're 0 miles from where we started, which means the last point on the graph goes just there. If we join these 2 points up, you'll see that we get a slope which has a negative gradient, which means that right up till 7 o'clock here, we were always further away from where we started. But at this point, as the distance from where we started began to fall, then we can realise that this here is our journey home.
A graph sloping upwards in this direction means you're travelling away. It's called a positive gradient. A horizontal line means you've stopped. A slope downwards in this direction means you're travelling back. It's a negative gradient.
Okay, this is the bit where Katie and I both tackle a typical maths question, but only one of us does it correctly.
The other makes a deliberate mistake which you have to spot. You decide, do you tick it or trash it?
Now, this week's problem is about someone's unfortunate journey to the shops.
An unlucky teacher leaves school at 12:30 p.m. and drives 3 miles to the shops. He gets a puncture and has to walk all the way back. What's the average speed of his return journey? Giving your answer in miles per hour.
An unlucky teacher leaves school at 12:30 and drives 3 miles to the shops. He gets a puncture and has to walk all the way back. What's the average speed of his return journey? Giving your answer in miles per hour.
Speed is distance travelled divided by time taken. The distance travelled from the shops back to school is 3 miles. To find the time taken, I had to read it off the graph. It's 6, 12, 18, 24, 30, 36, 42, 48. So 48 minutes. 3 divided by 48 is 0.0625 miles per minute. And to convert it to miles per hour, I multiplied by 60 to give an answer of 3.75 miles per hour.
I used the same equation. The distance travelled is 3 miles, but I reckon that the time taken is 5, 10, 15, 20, 25, 30, 35, 40 minutes. So that means 3 divided by 40, which equals 0.075 miles per minute. So multiplied by 60, and that's an answer of 4.5 miles per hour.
So which is right and which is wrong? Who read the time off the graph correctly?
Was Katie correct with 48 minutes?
Or was Ben correct with 40 minutes?
I was wrong. I made a mistake with reading off the units. I thought that each of these squares was equal to 5 minutes, when in fact each square represents 6 minutes. Count the number of squares per hour and the answer is 10. Now there's 60 minutes in an hour, divided by 10, that's 6. So it's 6 minutes per square.
It's easy to make mistakes about the scale and units of a graph, so watch out. Take time to read the scale carefully. Doesn't hit puppy. Yummy, yummy, yum, yum. This has been my stay in Brussels, but sadly it's now time to get back on the train and go back to London. Now we've got to travel 375 kilometres, and the Eurostar's top speed is actually 300 kilometres per hour. Now if we're to leave on time at 2 o'clock and we were to travel at that top speed, how long would it take us to get back to Waterloo in London?